This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today, we'll be delving into a research paper exploring implicit reasoning in deep time series forecasting. The authors investigate whether the impressive zero-shot forecasting capabilities of time series foundation models, TSFMs, stem from genuine understanding of temporal dynamics or simply from memorization of training data. What are your initial thoughts on this central research question? What are the potential implications of the findings, particularly for the development of future TSFMs?
The question of memorization versus true understanding is crucial for the field. If TSFMs primarily memorize patterns, their generalization to out-of-distribution OD data will be limited, hindering their practical applicability. The implications are significant. A model that truly understands temporal dynamics should be more robust, efficient, requiring fewer parameters, and capable of handling novel situations with limited data. The findings could guide the design of more effective architectures and training strategies.
The paper explores three forms of implicit reasoning: composition, comparison, and inverse search. Can you elaborate on how these tasks were designed to differentiate between memorization and genuine understanding? What specific challenges do these tasks present to the models?
The tasks are designed to force the models to manipulate knowledge in ways that go beyond simple pattern matching. Composition requires combining multiple time series in novel ways: addition, subtraction, multiplication, etc., testing the model's ability to synthesize information. Comparison involves forecasting series with parameter values outside the training range, assessing its ability to extrapolate and make comparative judgments. Inverse search challenges the model to decompose a composite series into its individual components, requiring a deeper understanding of the underlying structure. The challenge lies in the models needing to generalize beyond the specific patterns seen during training and apply learned principles to unseen combinations and variations.
The paper evaluates several model architectures, including linear models, MLPs, and various transformer-based models. What were the key differences in performance across these architectures, and what insights do these differences provide regarding the relationship between architecture and implicit reasoning capabilities?
The results showed a mixed bag. Patch TST, a patch-based transformer model, excelled at composition tasks, particularly addition and subtraction, suggesting that the patching mechanism helps in knowledge manipulation. However, its performance was sensitive to patch length, highlighting the importance of architectural hyperparameter tuning. D-linear performed well in addition, subtraction, and comparison, while NHIs showed strength in multiplication, function composition, and inverse search. This suggests that hierarchical architectures, like NHITs, and the specific way temporal dependencies are modeled, as in D-linear, can significantly impact the model's ability to perform implicit reasoning. The variations in performance across architectures underscore the need for further research into optimal designs for TSF-MILs.
The paper mentions that the patch TST model's performance on composition tasks was sensitive to patch length. Can you elaborate on this finding? What does this suggest about the role of receptive field size in implicit reasoning?
The sensitivity to patch length indicates that the model's ability to effectively compose time series is directly related to the amount of contextual information it can access at once. A larger patch length allows the model to consider more of the time series history and relationships between different parts, which is crucial for complex composition tasks. This suggests that a carefully chosen receptive field size is essential for enabling the model to capture the necessary temporal dependencies and relationships for successful implicit reasoning. Too small, and it lacks context. Too large, and it might overfit or become computationally expensive.
The paper also highlights the limitations of using traditional loss functions like may to fully capture the quality of forecasts in complex tasks. What are the limitations of may in this context, and what alternative evaluation metrics might be more suitable?
May, while a standard metric, only measures the average absolute difference between predicted and actual values. It doesn't capture the pattern of the forecast. For instance, a model might have a low may, but still produce a completely unrealistic forecast, for example, a straight line instead of a complex waveform. More sophisticated metrics that assess the similarity of temporal patterns, such as dynamic time warping, DTW, or metrics based on spectral analysis, could provide a more comprehensive evaluation of the model's ability to perform implicit reasoning. Furthermore, qualitative analysis of the generated forecasts is crucial to understand the model's behavior.
The paper concludes that linear, MLP-based, and patch-based transformer models exhibit implicit reasoning capabilities beyond symbol memorization. What are the broader implications of this finding for the field of time series forecasting, and what are some promising avenues for future research?
This finding suggests that TSFMs have untapped potential for more sophisticated tasks than previously thought. Future research should focus on developing more advanced architectures that explicitly encourage implicit reasoning, exploring novel training strategies that promote generalization, and developing more robust evaluation metrics that go beyond simple error measures. Investigating the interplay between architecture, training data, and evaluation metrics is crucial for unlocking the full potential of TSFMs in handling complex, real-world time series data. The development of more interpretable models is also vital to understand how these models are reasoning, allowing for better debugging and refinement.
The paper uses synthetic data. What are the limitations of using synthetic data for evaluating implicit reasoning, and how could future work address these limitations? What are the challenges in applying these findings to real-world data sets?
Synthetic data allows for controlled experiments, isolating specific aspects of implicit reasoning. However, it may not fully capture the complexity and nuances of real-world time series. Real-world data often contains noise, missing values, and non-stationary patterns that synthetic data might not adequately represent. Future work should incorporate more realistic synthetic data generation techniques that better mimic real-world characteristics, and ultimately, rigorous evaluation on diverse real-world data sets is essential to validate the findings. The challenges in applying these findings to real-world data sets include the high dimensionality, noise, and the difficulty in defining clear ground truth for implicit reasoning tasks in complex real-world scenarios.
The paper mentions several existing TSFMs, Chronos, Lagalama, Moirai, Moment, TimesFM, TimeGPT. How do the findings of this paper relate to the capabilities of these existing models? What are the potential improvements or modifications that could be made to these models based on the insights gained?
The paper's findings suggest that some existing TSFMs might be relying more on memorization than implicit reasoning. For example, while Chronos shows strong performance on composite series, it struggles with exponential trends. This paper's results suggest that incorporating architectural features like patching, as seen in Moment and Times FM, or hierarchical structures, as in NHIs, could enhance the reasoning capabilities of these models. Further research is needed to determine how to best integrate these insights into existing TSFM architectures to improve their robustness and generalization abilities. The key is to move beyond simply scaling up model size and focus on architectural innovations that promote genuine understanding of temporal dynamics.
The paper focuses on forecasting. Could the findings and methodologies be extended to other time series tasks, such as anomaly detection or classification? What modifications would be necessary?
Absolutely. The concepts of composition, comparison, and inverse search could be adapted to other time series tasks. For anomaly detection, composition could involve creating synthetic anomalies by combining normal patterns with unusual events. Comparison could involve detecting anomalies based on deviations from expected patterns. Inverse search could be used to decompose a time series into its underlying components to identify anomalous components. For classification, composition could involve creating synthetic examples of different classes by combining features. Comparison could involve classifying time series based on their similarity to known classes. Inverse search could be used to extract relevant features for classification. The key adaptation would be in defining appropriate tasks and metrics that align with the specific goals of each task.
The authors use a relatively small set of basis functions to generate their synthetic data. How might the results change if a more diverse and complex set of basis functions were used? What are the implications for scalability and computational cost?
Using a more diverse and complex set of basis functions would make the implicit reasoning tasks significantly more challenging. It would require the models to learn more abstract representations of temporal dynamics and generalize to a wider range of patterns. This could lead to improved generalization, but also increased computational cost and potentially longer training times. The scalability of the approach would depend on the chosen model architecture and the efficiency of the training process. It's a trade-off between the complexity of the tasks and the computational resources required.
The paper focuses on zero-shot forecasting. How would the results differ if the models were fine-tuned on a small amount of O data? What is the optimal balance between pre-training and fine-tuning for achieving robust O generalization?
Fine-tuning on a small amount of O data could significantly improve performance, especially for tasks where the O data is similar to the training data. However, overfitting to the limited O data is a risk. The optimal balance between pre-training and fine-tuning is an active area of research and depends on several factors, including the size and diversity of the pre-training data, the similarity between the pre-training and O data, and the complexity of the task. Transfer learning techniques could be explored to leverage knowledge learned during pre-training while effectively adapting to the O data.
The paper primarily focuses on the performance of individual models. Could ensemble methods be used to further improve the robustness and accuracy of implicit reasoning in time series forecasting? What are the potential benefits and challenges of using ensemble methods in this context?
Ensemble methods, which combine predictions from multiple models, often improve robustness and accuracy. In the context of implicit reasoning, an ensemble could leverage the strengths of different architectures, potentially mitigating the weaknesses of individual models. For example, combining a model strong in composition with one strong in comparison could lead to a more comprehensive and robust system. The challenges include the increased computational cost and the need for effective ensemble techniques that appropriately weigh the contributions of individual models. Research into ensemble methods specifically tailored for implicit reasoning in time series is a promising area.
This has been a very insightful discussion. Thank you for your expertise.